thank you for coming to this talk. My name is Michael Stockett, and I'm currently a final year PhD student at University College Dublin, working in the area of advanced formulation and associated manufacturing techniques. I'm funded by the Irish Research Council, and I'm also an associated student of the SSPC. Issues presented by the poor physicochemical properties of APIs are becoming increasingly prevalent in drug development, and are particularly apparent when attempting to formulate APIs for oral delivery. The low solubility of many candidate molecules corresponds to low in vivo exposure of the active compound, and so is a significant contributor to the high attrition rate of potential APIs. In addressing this, using higher energy forms of APIs is becoming more commonplace, which, whilst they might be more soluble, they are also more likely to be unstable and undergo polymorphic transformations during storage and administration. These two issues form the crux of the problem that formulation scientists have to solve: how to balance the efficacy of the solid form with polymorphic stability, and at the same time do so in a way that can be feasibly manufactured. Technologies that have previously tried to solve this problem include forming amorphous solid dispersions of APIs in polymers, micronization, and emulsification. However, these all come with their own drawbacks. One possible solution to these limitations is to use a seemingly unrelated family of compounds called ionic liquids. Conventionally viewed as next-generation green solvents due to their characteristic negligible vapor pressures and low flammabilities, ILs are seeing a surge of interest with regard to their applications in drug delivery systems. Ionic liquids are a class of compounds with a huge amount of promise for simultaneously addressing the issues posed by poor aqueous solubility of APIs and the issues of solid-state instability by forming a thermodynamically stable liquid form of the drug. As APIs are often large, bulky, asymmetric molecules containing aromatic and ionizable groups, they readily lend themselves to forming ionic liquids. To do this, we can exchange the metal or halide ion of a conventional salt for one such as an imidazolium or colinium ions, or even look towards artificial sweeteners such as saccharin to form ILs with cationic drugs. However, as ionic liquids are often viscous oils or hygroscopic waxes at room temperature, there are still considerable barriers to be overcome if they are to be routinely incorporated into solid dosage forms. Methods for solidifying API-ILs that have been previously reported include immobilizing them in ionogels or mesoporous silica. However, as gels cannot be readily incorporated into existing formulation process streams, and the silica approach struggles to achieve complete desorption from the solid carrier, a more practical means of solidifying API-ILs remains to be found before they can be routinely incorporated into solid dosage forms. To address this, we've developed a platform that uses spray drying to solidify API-ILs by forming a solid solution of API-IL in a miscible carrier or spray encapsulate it in an immiscible polymer. This approach was developed initially using the model compound 1-butyl-3-methyl imidazolium ibuprofenate, which is representative of API-ILs as it has a melting point of -26 degrees Celsius and is a viscous oil under ambient conditions. The most obvious approach for solidifying IL drugs via a direct spray process is to combine it with the polymer carrier to create a single-phase solid solution similar to what is achieved when producing amorphous solid dispersions of APIs. Using this method, we've been able to successfully solidify the IL by combining it with a polymer that has an unusually high glass transition temperature that offsets the extremely low melting point of the IL. The polymer found most suitable for this was maltodextrin, and we were able to successfully form a solid solution of the two components at a benchmark value of 50% weight-for-weight ionic liquid, with the recovered content being a fine white powder. However, even at marginally higher loadings, the glass transition temperature suppression becomes too substantial to recover a solid product. Unfortunately, our ability to work around this using lower processing temperatures is severely limited by maltodextrin's extremely low solubility in even small amounts of organic solvents. Powder X-ray diffraction was used to verify that the material produced conserves the liquid form of the API as amorphous materials. The diffractograms presented here show this to be true for both grades of maltodextrin by the diffuse halo patterns and absence of Bragg peaks. Calculated DSC shows that the API-IL is miscible with maltodextrin from the single broad glass transition temperatures that lie between those of the pure components, with points taken as the TGs shown by arrows in the graphic. For this API-IL, the TG is the same as the melting point, and as the solid product was recovered from the spray dry, this shows that it is possible to solidify an exceptionally low melting point drug by an appropriate selection of high TG polymers. Spray drying a solution containing the drug-based IL and an immiscible polymer such as ethyl cellulose allows for a remarkably high amount of IL to be contained in the powder. When produced in this way, we can solidify up to 75% weight-for-weight IL as a fine white powder and recover it as a solid at up to 90% weight-for-weight loading. At this extremely high loading, the product becomes more of a paste, and so this is taken to be the failure point of the system. From in vitro dissolution studies, we have found that the performance of the IL form of the drug is not impeded when combined with the polymer in this way, and so this allows us to design ILs with more regard to their in vivo performance without having to consider any detrimental physical properties that might result from this. As the polymer is phase separated from the IL and not interacting with it in any significant way, the performance improvements can be attributed solely to the drug being in the IL form. This is advantageous as there is no so-called spring and parachute effect required from the carrier polymer as would be expected in an amorphous solid dispersion, so it demonstrates that the stability and solubility enhancements are thermodynamically stable as opposed to kinetic. As with the miscible systems, PXRD was used to ascertain whether the liquid form of the API afforded by the IL was preserved during the spray drying process for the immiscible systems. Again, the diffuse halos and absence of Bragg peaks confirm this for both grades of ethyl cellulose and for all ratios of API-IL to polymer studied. Low molecular weight grades exhibit diffuse peak maxima at approximately 8.5 and 21.5 degrees 2 theta, while the maximum value for the API-IL can also be found at 21.5 degrees 2 theta. Dried products with higher ratios of API-IL to polymer show a gradual decrease in the intensity of the peak at 8.5 degrees 2 theta, while the peak at 21.5 degrees 2 theta remains unchanged. Similar composition dependence of the amorphous halos has previously been described in the literature as being indicative of phase separation. The DSC thermograms for the immiscible systems exhibit a single glass transition temperature for all the ratios studied. Ordinarily, this would be taken as evidence of a miscible system. However, the behavior of the system is somewhat unusual, as even with high proportions of polymer, the single TG is remarkably close to that of the pure API-IL and shows no dependence on the composition of the system. Considering the conventional application of ILs as solvents, one possible explanation is that the API-IL and polymer are initially phase separated, but upon heating over the course of the DSC experiment, the API-IL is able to dissolve the polymer. As heats of solution are generally of low energy, and so likely below the limit of detection of the instrument, this would explain why no additional thermal events are observed. To investigate this theory, hot stage microscopy was used to monitor the nature of the material as it undergoes heating. In this example, the product composed of the low molecular weight polymer and containing 50% weight-for-weight API-IL confirms the hypothesis. Initially, the formulation appears to be a solid powder, until a liquid emanates from it at around 85 degrees C. Heating the sample further, we can see that the liquid starts to dissolve the polymer at around 115 degrees C and completely solvates it by 125 degrees C. These observations were true for all compositions and verified that the API-IL is initially phase separated from the polymer. As a demonstration of the improvements over amorphous solid dispersions, dissolution tests were carried out in deionized water. Here, it can be seen that all the powders containing the IL form of the API greatly outperform both the crystalline form and an analogous ASD, even when contained in a water-insoluble polymer. Full or close to full release of the API can be attained with all loadings and is irrespective of polymer grade. With the IL form of the drug, we found that it remained stable in concentrations ranging from 2 to 85% weight for weight in deionized water and simulated intestinal fluid for 2 years, with no evidence of crystallization or phase separation. At ratios above 50% weight for weight IL content, the dissolution media is now being solvated by the drug, which, in its free acid crystalline form, has a solubility of 0.068 mg per ml in deionized water. This is a remarkable improvement over ASDs, which only provide short-term stability and dissolution enhancement. Additionally, ASDs require a high ratio of polymer to API to prevent recrystallization of the drug or amorphous phase separation, and so limits the amount of API that can be feasibly incorporated into a solid dosage form. This has largely been addressed by the IL approach outlined here, and shows the potential of this integrated purification approach by enabling significant new possibilities in engineering API forms. The number of ionic liquids that can potentially be formed has been estimated to be higher than 10 to the power of 14, and so there is a huge amount of scope for developing API-derived ILs. With this in mind, a number of additional API-ILs were spray-dried using the immiscible approach to demonstrate its versatility at 50 and 75% weight-for-weight loading in the high molecular weight grade of the polymer. In the diffraction patterns presented here, the pure API-IL is the lowest graph for each example, with the 50% weight-for-weight loading placed above it, and the 75% weight-for-weight loading located above that again. As expected, there is no evidence of crystalline material for any of the products after being spray encapsulated. Interestingly, there appear to be some small crystalline peaks in the pure co-IBU API-IL. This is attributed to the material being crystalline initially, but deliquescing as the measurement is being taken, which was also observed when preparing the material for spray drying. Nonetheless, there is no crystalline material in the spray-dried products for this example. Thermograms of the additional API-ILs, the order of the compositions is the same as in the PXRD results. Here, the phase-separated nature of the products is even more apparent than for the initial imidazolium-based API-IL from the presence of a second TG where that of the polymer is expected to lie. Again, the co-IBU example presents behavior inconsistent with the other examples. This is explained by co-IBU being only partially dried during the initial DSC drying cycle, and the residual moisture in the final heating cycle results in the API-IL partially recrystallizing into two distinct polymorphic forms. This has previously been observed for this API-IL and is mirrored in the thermograms of the spray-dried products containing this example. Here, two methods of solidifying API-ILs using spray drying processes have been presented. Using maltodextrins as high glass transition temperature polymers, it is possible to form solid solutions of room temperature API-ILs that can be recovered from the spray drying process. This approach allows up to 50% weight-for-weight loading of the liquid drug, but unfortunately is limited by the poor solubility of the polymer in organic solvents. Alternatively, we can use phase-separated systems to encapsulate API-ILs at really high loadings, with no effect on the dissolution behavior of the drug. This has been shown to be a versatile approach and allows for API-ILs to be designed for optimum in vivo performance with no regard for their physical properties. Collectively, using spray drying to solidify these kinds of materials presents a means from which we can further formulate API-ILs and for their true potential as drug delivery tools to be realized. Thank you very much for your attention. If you have any further questions, please feel free to reach out to me via the email address provided below. Thanks.